All right, welcome to Comp 2140. We're going to get started right away. First of all, introductions. I'm your instructor, Zoe. Pronouns she, her. Never know how much to talk about this. I'm trans. It's like a big part of my identity, but I don't want to make a big deal out of it. I'm here to teach you computer science, not biology or political science, chemistry. So I'll just leave it at that. Use she, her. Thank you very much. Lectures are right now an hour and 15 minutes per lecture, Mondays, Tuesdays, Wednesdays, and Thursdays. It's basically the same schedule as a Tuesday-Thursday class in the sense that lectures are an hour and 15 minutes, but instead of 2 days a week, it's 4 days a week, and as such, the class goes at double speed. Office hours are right after each lecture. My office is E2 422A. There is 1 day, or I guess 2 days, this term that don't conform to this schedule. There's a holiday sometime this month. I think it's like the 15th or something, somewhere in there. We're going to have Monday off and then a makeup class on Friday. So you could imagine this slide saying Mondays, Tuesdays, Wednesdays, and that one Friday, and also not that one Monday. You'll get it. The course syllabus and schedule are posted on UM Learn. It says here, please read these documents carefully. Excellent suggestion. We're going to spend a decent chunk of this lecture just going through the syllabus. So here I am on the course homepage. You should be able to access it. If you can't, that's kind of a big problem. Everything for this course will be distributed through that webpage. So let me know after class if you're not able to access it. Also, on a similar note, I'm aware that there's a humongous wait list for this course. I think it's like larger than the course itself. So if you're on the wait list and wanting to keep up with course content while you're hopefully going to get into the course, you can talk to me and I could add you as an auditing student. That way you won't be like officially in the course. There are no shortcuts. You can't cheat the wait list. But you'll be able to access everything. So anyway, you could find the syllabus at content. I don't think it'll be that fast, you guys. I think you'll have to start at table of contents, and then under syllabus and schedule, we have the big one. So, why are we all here? Why are we learning about data structures? What even is a data structure? You'll learn that eventually, not in the first 2 weeks. I'll get into why later. But the content of this course, it turns out, forms the backbone of pretty much any interesting program ever made in the real world. And I can exaggerate things a lot, but that's not even an exaggeration. And a bit more cynically, but I really should acknowledge it, this thing called LeetCode. Job interviewers love it. It's like candy to them. And a lot of those questions from LeetCode that they assign during job interviews, those revolve around smart use of data structures, because choosing the right data structure can be the difference between code that's efficient and code that crashes when your website gets even like 100 users. So if nothing else, I hope you get more from this course than that. If nothing else, this can be the job interview course. So by the end, you'll be able to talk about abstract data types and how they differ from data structures, implement the most common abstract data types, You might have heard of some of these before, like stacks, queues, graphs. And then implement the data structures that are used to create realizations of the ADTs, like linked lists, search trees, so on. I'm throwing around a lot of terminology here. Don't worry, it'll be properly introduced during the lectures. And that last bullet point under, by the end of the course, students will, that is carrying a lot of weight because it was recently changed in the curriculum for like the whole computer science program to make this course a bit more theory focused. You'll become dreadfully familiar with what I mean over the next couple of weeks, but for now we can leave it at you will also analyze runtime and space requirements of data structures. There isn't a textbook, but you could get them on, well, there isn't a required textbook, but there are 2 free textbooks available on the course website. You probably won't need them. Last time I taught this course, I don't think I ever opened them after the first day, but you might. It's potentially useful supplemental info. Now for the course schedule. This part's gnarly. I really hope you all know what you're getting into because this course is condensed. 2 months instead of 4 months. And that means we're going to be covering a lot of content really quickly. About 2 weeks of content per week. And there are a million corollaries of that where you'll have half the time to do each assignment, half the time to study for each quiz, probably very little time between the last day of classes and the final exam as well. So we're going to go pretty fast. I don't think I'll go into detail on all of these topics, but I want to note the last 2 columns. There's going to be an assignment pretty much every week in this course. Get started early. And also the last day to drop courses without a penalty, so it'll just disappear from your transcript, is this Thursday. So I hope you're paying attention to get your first impressions because you have until the end of this week to decide whether you want to stay in the course or not. May 19th is that day I was thinking of. It's a holiday, no classes that day. We'll have a makeup class for that on Friday, the 23rd. And then the VW date is on June 5th. Thankfully, a lot more forgiving than the drop deadline, but a VW will stay on your transcript, as you probably know. This stuff's pretty boring. Basically says you need a computer. You could email me with any questions. There's also a discussion forum. The paragraph for that is right under the communication header. You can post things there with questions about assignments or general course content. And that's basically to make it so that no one has any insider information. No student gets an advantage by just asking more questions than others. If a student has a question and the answer will be useful to others, the discussion forum makes it so that everyone can see it. Consequentially, if you try emailing me a question about an assignment, I have a copied and pastable email locked and loaded saying, actually, can you post that on the discussion forum? I will send it. Don't cheat. Really good at detecting cheating, and there is pretty severe penalties for cheating. I guess this leads pretty naturally into the grading scheme because in terms of motivation not to cheat, there is the usual argument that like university is a place to learn, and by cheating you're upsetting the meaning of your degree or something. Basically, degrees will be devalued if employers see that that people are cheating through them. So that's all good. Hopefully that's enough motivation not to cheat. But if you're still feeling tempted to copy and paste assignment descriptions into AI, note that the final exam is worth 55% of your final grade. And I'm sure it says so somewhere, I think under a dedicated final exam section. You have to pass the final exam to pass the course. So the best way to study for the final exam is by doing the assignments yourself. And if you don't, it's very likely that you'll get cooked on the final. So if the thing about the sanctity of your degree didn't convince you not to cheat, hopefully the 55% final exam will. Also of note is just how the assessments will be structured. Wait. Did I say won't? I meant to say the thing about the final exam being 55% will convince you. Anyway, we're going to have assessments that's somewhat equally split up between assignments and quizzes. The assignments, as shown in the schedule above, have roughly 1 week turnaround times. Although you'll kind of sort of get 2 weeks to do assignment 1. I say kind of sort of because it just takes a week to give you the content that you need for that assignment. You don't really get any time advantage unless you already know what I'm about to teach you. But then assignment 4 gives you 2 weeks, and that's because it's a big one. Find out more next month, I guess. Oh, almost showed you guys the really scary part. I want to make it nice and clear before I show off the letter grade cutoffs. The way that assigning letter grades sort of works. So you're all familiar with letter grade cutoffs, like you need a 90 to get an A+, 80 to get an A, so on. After all grades are in for all assessments, instructors can, and almost all the time do, adjust letter grade cutoffs, but they can only decrease them. If we start off with a cutoff for A+ being 90%, they can turn it into 89%, but they can't turn it into 91%. I think that's just in the interest of fairness. We're allowed to pleasantly surprise students with a slightly better grade than they expected, but not to give them the unpleasant surprise of harsher evaluation than planned. So, because we can only decrease the grade cutoffs, it's common practice to set the grade cutoffs really high at first and then lower them afterwards in order to get a good distribution of grades across the class. So take a deep breath. This is the scary part. Ta-da. Don't take this too seriously. I'm almost certainly going to lower these. Back to assignments. There's going to be 4 of them. Each of them is worth 5% of your final grade. Ask questions on the discussion forum. There's a decently generous late policy. Late assignments will be accepted up to 48 hours late with a 5% penalty per day late. So assignments tend to be due on Fridays, so if you need some extra time, you can have until Sunday to submit with a slight penalty. I think it says later, if you're sick or you're busy or for any reason you can't complete an assignment, you can submit a self-declaration form for temporary absence. That will make it so I will shift the weight of that assessment over to the final exam when calculating your final grade. You can do this for assignments or quizzes, but you can only do it once. This is just university policy. I'm following it. Yeah, I think it's to reduce administrative workload of like verifying that students are in fact unable to complete assessments. But the way that this is implemented, you basically get one get out of jail free card. You can miss one assessment. Use it wisely. Going back up, there are going to be half-hour long quizzes at the end of each week. So this will give us roughly the same amount of in-person testing as if we had 2 term tests during the course. But it's more spread out. You'll be in pretty much a constant state of studying. And I'm conflicted between saying sorry as a fellow human for putting you through all this, but you're welcome as an instructor because I'm kind of forcing you to adopt effective study habits. If you get your grade back for an assessment and you think that there might have been a grading error, there will be a form on UMLearn that you can fill out to request to regrade. Note that the form will only be open for a somewhat short period of time, so it's up to you to look at your feedback promptly. Oh, that's where it says a passing grade on the final exam is required in order to pass a class. I knew I'd put it somewhere. Yep, and then the last little bit of the syllabus is copied and pasted from somewhere. Just standard information that applies to every course. Student Accessibility Services offers accommodations for students with disabilities. Content in this course is copyrighted, so don't copy it, not write. And there's a document right next to the syllabus containing a whole bunch of policies, resources, links that are as well standard to all courses in the university. Oh, okay, that's the syllabus. I realized partway through that aside from the whole gender thing, I'd never really told you all anything about myself, so I'll fix that now. So I'm a grad student. I did my undergrad at U of M. I took this course approximately 5 or 6 years ago. I'm doing my grad student work in the GADA lab, Geometric and Distributed Algorithms lab. And I'm studying a thing called the Busy Beaver problem. An incredibly interesting problem, but explaining any bit of it requires a huge info dump of background knowledge that we just don't have the time for. But I can say you should totally take Comp 3030, automata theory and formal languages. That's foundational for the Busy Beaver problem and a really cool course in general. Also, speaking of student accessibility services, a student in this class requires a volunteer note taker. Basically, you take notes as you already would be and upload them to a SAS portal at the end of each class. Really simple, pretty easy, but it makes a big positive impact for a student in this class. So highly recommend applying for this. Okay. Ready for content? Ooh. Actually, I'm going to procrastinate a little bit. Back to the syllabus. The course is 6 weeks long, and our first big topics are going to be about things that don't seem to have much of a clear connection to data structures and their implementation. We're going to be talking math, proof techniques, quantifiers, summations, and algorithm analysis. This was a relatively recent change in the curriculum for this course. Before, there was a theory course and a applications course. Now, those two courses still exist, but they're kind of a bit of both for each one. You're in data structures analysis and implementation right now. And the other course now features both theoretical and practical stuff about algorithms. Our first 2 weeks are going to focus on theory, and it is the hardest part of the course by far. I think it's structured this way because of the wait lists. If you don't like math, the first 2 weeks are going to be pretty hellish, and you might want to make room for someone else in the wait list. But I probably don't need to hype this up. This will speak for itself before too long. Oh, wait, one more thing. The connection from the theory to the practice, as it turns out, is that we're going to be analyzing properties of data structures. So for each data structure that we encounter in the course, there's going to be a mixture of practical applications, like how is this used in the real world, and mathematical stuff, basically backing up what we're talking about with proofs. So we know absolutely for sure what we're talking about. What is a proof, you may ask? There are many ways to state it. This slide says that a proof is an algorithm for proceeding from a set of axioms to a conclusion using the rules of mathematical logic. But that definition is a bit stuffy. If you already know what a proof is, this definition can reaffirm your intuition. But if you don't, it's not very helpful. So I would say that it's a formal argument for showing that some conclusion is true. And then I can't resist using that last clause, using the rules of mathematical logic. So in a proof, you start with some facts that you basically assume to be true, called axioms, and use those, build upon them, to come to some sort of conclusion. It's like the axioms are your Lego bricks and your conclusions are whatever you make with them. So our axioms can differ from place to place or from application to application. In this course, we're going to have our axioms defined somewhat informally, intuitively, but easy to get a grasp on. Our axioms are the real numbers work the way they always do. Another nice way to put it is that everything you learned in grade school still applies. Cool. There are many more advanced math courses and mathematical topics where you can't assume that. You need to define your operations from first principles and write a 20-page proof that 1 plus 1 equals 2. Also that 1 equals 1. But you don't have to do that. Basic arithmetic, inequalities, properties of integers, and all the basic functions that you know are available for us to use. So, knowing what statements require, or what statements don't require proofs, sort of raises the questions of what statements do require proofs. I guess going back to what statements don't require proofs, statements about specific numbers don't require proofs. So like the fact that a certain number is a divisor of some other number, or that some number is prime, those can be stated without further justification. But there will inevitably be disagreements over whether or not it's okay to just say that something is true. This is obvious, this is clear. So if you're not sure, just err on the side of showing your steps. You'll never lose marks for explaining specifically why 3 is a divisor of 7. But you might lose marks if you use, I don't know, I can't think of an example without bringing up topics that you've never heard of yet. So we're going to go through some examples of proofs in this class. And this all so far, and for the next couple hours of lecture content, will hopefully be a review from an introductory discrete math course, most likely Comp 1240. So if you've taken that class already, you can relax a little, but only a little, because it's going to get much harder pretty quickly. And if you haven't taken Math 1240, then this first bit of the course is going to be even worse than I've been hyping up. However, not hopeless. There are lots and lots of readings for the course. None of these are required. You'll never be tested on you'll never be tested specifically about any of the stuff in the readings. But these are all foundational. So if you're not familiar with what mathematical logic is, then you better check out the reading Logic 1 and Logic 2. These readings have more review content about proof techniques. You don't have to read all of these right now. I think everything up to proofs 1 and 2 solutions cover the first and second lectures, and then summations, analysis, and cost functions cover the next 2 lectures of this week. Again, this is a lot of readings. I'm going to keep mentioning it. This course is at double speed, and the first bit of the course was pretty hard even to begin with. So drop it if you feel like it. But if you're ready to persevere and go through the whole course, know that the readings and the math ease up significantly after the last few weeks. This is the most readings in any week of the course by far. I think week 2 has like 4 readings, and then the remaining weeks have none. Back to the class. We're gonna first cover how to prove an AND statement. So that's any well-formed mathematical statement that states that 2 things are true at the same time. So the thing we're going to prove for our example is, assuming that x is an even integer, prove that x squared is even and x cubed is even. If you think about how you would prove this yourself, you might run into a roadblock pretty quickly, and that's how to express that something is even. Ignoring the definition at the bottom of the slide, because the conclusion I'm eventually going to make is that the definition at the bottom of the slide is really useful. You might start out thinking, well, what did I learn in kindergarten? An even number ends with either 0, 2, 4, or 8. That's good. That definition does cover all even integers without any nasty counterexamples. But proving this statement with that definition would be super clunky. I think you'd have to split it up into cases and then prove the statement for numbers that end in 0, and then prove the statement for numbers that end in 2, and then do it for 6 and for 8. Blah. So this is kind of a big lesson hidden in this rather innocuous example. It's that definitions are super important. You need precise, correct definitions to really do anything with math. And that brings us to the canonical definition of what an even or an odd number is. An integer x is even if there is another integer a such that x equals 2a. I'll just quickly run through a couple of examples for that. 4 is even. We all love 4. Four equals 2 times 2. So if we say that a equals 2, then we get an expression of the form x equals 2a, because 4 equals 2 times 2. Let's do a pretty big number, 512. Intuitively, we know it's even. It ends in 2. But these definitions allow us to reason about them more effectively, so it's still worth going through this example. That's 2 times 256. So x equals 2a. 512 equals 2 times 256. It works. Similarly, x is odd if there's another integer a such that x equals 2a plus 1. Whoa! Yeah, it does that sometimes. So let's use as an example 9. So 9 equals 2 plus 4, or 2 times 4 plus 1. So in this case, we would say that A equals 4. You see in this? I don't feel like doing an example with big numbers. It's a miracle that I remembered 512 is 2 times 256. Only thing I want to note before we move on is that it's impossible, using these definitions, to accidentally classify an odd number as even or an even number as odd. You'll never find an integer such that 9 equals 2 times that integer. So now that we have these definitions, we can probably move on with the proof, although I think that there's a bit more we might have to explain to do with how exactly to handle that and. It's implicit. Okay, I'm going to talk a bit more before going on to the solution. When a mathematical statement says that something is true and something else is true, and you need to prove that, you can do that by basically proving the two sides of that statement separately. There are going to be similar rules for or statements, but they're a bit more complicated, so make sure you understand the example of and before moving on. So in this case, x squared is even and x cubed is even. We're going to show separately we're basically going to show two implications separately. Showing separately that if x is even, then x squared is even, and that if x is even, then x cubed is even, is equivalent to showing that if x is even, then x squared and x cubed are both even. So let's go through the proof. This is also a decent example of proof structure. In this course, you'll be writing a lot of proofs, and it's recommended, though not required, you won't lose marks for not doing this, that you sort of number your steps. It's like splitting up blocks of text into paragraphs when you're just writing normal stuff, or splitting code into functions when you're writing code. It just splits up your logic into more understandable chunks, and it lets you easily refer to little things that you've proved already. Another useful, generalizable aspect of this proof is that the first step of it is basically just repeating a definition. This first step, it doesn't really do anything. It's just making it really clear that x is an even integer, and by definition of even, that means that a exists, and that x equals 2a. Second step provides an example of the thing I was saying earlier, that we can easily refer back to previous small conclusions made in the proof. It's much easier and more elegant to say, from step one, we get this, than it is to say, from the definition of even, which states that there is an integer a such that x equals 2a, we get, no, don't do that. Just say, from step one, every time you have to refer to step one. Another thing that I want to point out about this proof is that it uses our axioms. Yeah, like there isn't really much to gain from the proof itself, but there's a lot about this proof that is worth highlighting to help you write your own proofs later. So, uses our axioms. What do I mean by this? Well, this first step of this equality manipulation, x squared equals 2a squared, that's just substituting one value for an equal one. That's fine. But then 2a squared equals 4a squared? What? If this were some like third or fourth year math course and you haven't proved that by first principles yet, you'd be laughed out of the room. But luckily, we can assume that everything from grade school works as you'd expect. So you probably learned about the distributive property of exponentials over multiplication at some point in high school, and you can just use it. 2a squared, or 2a squared equals 4a squared. Everyone knows this. And then we use the groundbreaking fact that 4 equals 2 times 2. Again, this is an example of grade school math being just readily available for us. You'd have to prove that from first principles in a more advanced context, but you don't have to here. And from 4a squared, we get 2 times 2a squared. I promise I'll stop noting this eventually, but here's another example of properties of integers and how you can just take them for granted. Since a is an integer, it follows that 2a squared is also an integer. Do you have to prove that multiplication and exponentiation are closed under the integers? Do you have to know what closed even means? Nope. You learned this in grade school. It's decently intuitive, so you can use it in a proof. 2a squared is an integer. And because we just expressed x squared as 2 times 2a squared, that's 2 times an integer. The wording can get awkward because we already have a variable called a, but it hopefully won't take too much effort to generalize the definition we saw above and find that expressing x squared as 2 times 2a squared fulfills the definition of even, 2 times some integer. And then you can conclude that x squared is even. Yippee! So we've proven so far that if x is even, then x squared is even. To finish our proof, it remains to show that if x is even, then x cubed is even. And that follows a pretty similar argument. It might be nice practice to do this proof yourself on your own. It has absolutely nothing to do with data structures, but it has everything to do with proof structure and use of axioms, and thus will be foundational for further study on this. So yeah, this third step works pretty much the same way. Invoke step 1 to use the definition of even and get an integer a, such that x equals 2a. Cube that. 2a cubed is equal to 8a cubed. And then you could split that into 2 times 4a cubed. Woohoo! Since a is an integer, it follows that 4a cubed is an integer. We just found that x cubed equals 2 times some integer. Therefore, x cubed is even. Last thing to note about this proof is how step 4 kind of reminds me of step 1 in the sense that it doesn't do anything. Steps 1 and 4 are like the cover page and the back cover of our book. They don't provide any additional content, but they're still useful to have because proofs are a communication tool. You could imagine a super long, 200-step proof going on and on and on and on about something. By the end of it, you forget what you were even proving. And as such, it's helpful to have that last step just explain what just happened. Thus, x squared is even and x cubed is even. That second thing we basically already talked about, but this notation is going to come up later. Who has time to write 3 entire letters? Not me. The notation that mathematicians usually use is this little triangle. P, that little triangle, Q, means P and Q. And then the second thing is, again, what we've talked about. If you have two true statements and you prove them both, you can conclude that the first statement and the second statement are both true. Next up is OR statements. I've been hyping up how hard this course is a bit, but I think this is sort of the first thing to truly trip students up. So I want you to really internalize this line. But I'm getting ahead of myself. I'll explain why that line is important right away. As an exercise in proving an OR statement, we're going to show that if x is a real number such that x squared equals 25, then x is less than or equal to 5. So that brings us to the thing that I said trips people up. X is less than or equal to 5 means that x is less than 5 or x is equal to 5. Later on in the proof, And at many points during the course, we're going to say stuff like, since x is less than 5, this means that x is less than or equal to 5. And then people go like, huh? No, but it's true. When you have an or statement like this, it means that one of the sort of component statements that make up the big statement is true. So this feels kind of basic now that I've written out this little table, but trust me, we're going to be working with a lot of inequalities in this course, and they're going to get so much more complicated than x is less than or equal to 5. So it's worth getting a really good grasp on the basics. Actually, I'm going to make this table even bigger. And we're going to use T and F to denote true and false, just to keep the table nice and tidy. So 3, is that less than 5? Yes, that's true. Is it equal to 5? No. False. Is it less than or equal to 5? Yes. I'm going to speed through the next few rows. Five is not less than itself, but it is equal to itself. So we just made a sort of rudimentary truth table. Hopefully you know what truth tables are from Math 1240. If you don't, check out the readings. We see that the statement x is less than or equal to 5 is true if one of x is less than 5 and x equal to 5 is true. This means that something that might initially sound kind of BS-y like this is actually totally true, because in all cases, if x is less than 5, then you can safely conclude that x is less than or equal to 5. Of course, this truth table is absolutely not a proof. If you hand in a proof that is composed of 5 examples of integers that the statement applies to, the marker will get very mad at you. This is just an illustration of why we're taking certain logical steps in our proof. All right. Step 1 also illustrates a way to, or rather the way, to prove an implication that starts with an or statement. Or, no, I'm overcomplicating things. It shows a useful technique for proving things when one of a few options are true. In this case, we were told to assume that x is a real number such that x squared is 25. This means, by our axioms again, that either x equals 5 or x equals negative 5. We know from high school that there are no other possibilities. So it would be pretty clunky to go ahead with the proof in just like one path. So going like, since x equals 5 or negative 5, we can conclude that, no, just do them separately. Yeah, I'm going to draw something on the following slide. Bit of an explanation of what I'm doing. We have some similar notation to that and thing. No one has time to type 2 entire letters. P or Q is often written using this sort of V shape. The way I like to remember it is that and starts with A, so its symbol looks like A, and then or is like the counterpart to and, so you do an upside down and symbol. So what's that thing that I just wrote? Well, first of all, this symbol is logical equivalence. Basically, if the left statement is true, then the right statement is true, and vice versa. If the right statement is true, then the left is true. This is like a general rule for proofs by cases. If you want to show that if one thing or another thing gives you a conclusion, so if x equals 5 or x equals negative 5, then x is less than or equal to 5. That's equivalent to showing separately that the first statement implies the conclusion, and that the second statement also implies the conclusion. Basically showing that no matter what ends up happening, you're going to be right in the end. So let's get back to our proof. We proceed by cases. Case 1 is that x is equal to 5. Well, clearly it is. Going back to axioms again, that's the kind of thing that you could just say is true. And then step 3 is a bit more complicated, but still manageable, I hope. If x is equal to negative 5, then it's less than 5. And because of how or statements work, the fact that x is less than 5 means that it's less than or equal to 5. Wow. And then step 4 is our cover page, our conclusion. It doesn't really do anything, but it's really nice to have. And when you're doing stuff like assignments for school, you kind of want to help out the marker as much as possible, provide as good an experience for them as possible. And part of that is making your proof really easy to understand for them, which you can accomplish by writing a sort of concluding statement like this one. The second point on this slide is sort of like a generalization of that less than or equal to 5 thing. And it can get pretty weird, but it's worth noting, especially if you don't understand that less than or equal to thing yet, because it can help you figure that part out. So if we have proved P, then for any statement Q, we can conclude P or Q. So, So how about this is P. We have something that's obviously true. 2 is an integer. It's one of the best integers. And we can say P or something ridiculous, something that would get us fired. Like 0 equals 1. That's our Q. So that's a true statement. 2 is an integer or 0 equals 1. Check out the readings if you think I'm bullshitting. The or symbol just requires that one of the 2 statements on either side of it is true. So P is true, and thus P or Q is true. And then the third point is the thing I illustrated below. If we know P or Q, then we can proceed by cases, show separately that P implies R and that Q implies R. And that shows you that if P or Q, then R. R. I think this is our last example. No, we have at least one more. So this is proving an OR statement. And this is an example of another technique that you're going to use later in this course. So if we assume that x plus y equals 10, we can show that either x is less than 5 or y is x is less than or equal to 5 or y is less than or equal to 5. You could probably convince yourself of this intuitively on your own. If 2 numbers equal 10, then they can't both be greater than 5. One of them has to be less than or equal to 5. So how do we prove this? As always, it would be clunky to attempt to prove this directly. How do you even show that at least one of these things is true? We're going to use a trick that sort of takes advantage of the definitions, of the definition of OR that we're using. And that is to suppose that one part of the OR statement is false. So what are we doing here? We want to show that either x is less than or equal to 5 or y is less than or equal to 5. If this whole thing is true, then at least one of these smaller statements, x is less than or equal to 5 and y is less than or equal to 5, is true. So you know that one of them is true. You don't know which one, but you can say that if one of them is true, then the other must be true. Because if they were both false, then the whole thing would be false. So suppose that x is not less than or equal to 5. This is equivalent to saying that x is greater than 5. And then from there, it's kind of just algebra. You can subtract x from both sides to make it so the equation is in terms of y. And then substitute the value of x to make it so 10 minus x is less than 10 minus 5. And from there, you know that x is less than 5. And then this brings back the thing that I spent so long on the previous example. We found that y is less than 5, and this implies that y is less than or equal to 5. They're both true. And that, it turns out, is all you have to do. We showed that if x is not less than or equal to 5, then y is less than or equal to 5. And because of how OR is defined, using that proof technique means that the OR statement is true. We can just conclude that x is less than or equal to 5 or y is less than or equal to 5. You can also do a very similar proof with this exact same structure by assuming that the other side isn't true, assuming that x is greater than 5, and then using that to show that x is less than or equal to 5. So this slide sort of explains how exactly that technique works. Honestly, for the sake of this course, you could just accept that this rule works and move on. But it might be fun to make a truth table yourself for the sake of your own practice and show that this point is true. And yeah, that's sort of a proof by cases in disguise. If P is true, then P or Q follows immediately because one of the statements in the OR statement is true. And then if you suppose that P is not true and prove Q, then P or Q is true because Q is true. Cool. Since this is a standard argument, we omit the behind-the-scenes details and simply use the general rule above. Cool. Last thing I want to highlight from this slide is more notation. Not P is written with this thing. It kind of looks like P is holding a gun. Um, and that is equivalent to like the exclamation point sign when you're working with bool variables. You can write not P to write the opposite of P. If P is true, not P is false. If P is false, then not P is true. One more example. This is a proof by contradiction. And that is a technique for proving things that works if it's hard to do it directly. Like, it would be difficult to just start with x plus y is equal to 10 and then come up with the conclusion that x is less than 5 or x is less than or equal to 5 or y is less than or equal to 5. So we're actually going to assume the opposite of the conclusion we're trying to reach and show that it leads to something stupid. This is another rule that works sort of behind the scenes by using the definitions of our logical connectives. And I would recommend teaching yourself more about it on your own time. I hope you learned about it in Math 1240. But for this course, we're just going to sort of note that the technique exists and then use it as we please. This negation is using another thing that I'm going to gloss over, but is in the readings and was hopefully in a previous course. You can negate an or statement by getting the and of the negations of both sides of the or statement. So we suppose in order to obtain a contradiction that this is not true, which leads to x is greater than 5 and y is greater than 5. Then some algebra shows that x plus y is greater than 10, but this contradicts the thing that we assumed is true. Since we assumed that x plus y equals 10, finding that x plus y equals 10 is as good as saying 0 equals 1. It's false. So we've shown that if x plus y equals 10 and this whole thing is not true, then we get a contradiction. Math breaks. We all die. And this lets us conclude that if x plus y equals 10, then this thing is true, because assuming otherwise leads to a contradiction. It's pretty neat. This triple lines is the same thing as the thing I used earlier, which kind of looks like a less than sign, an equal sign, and a greater than sign. They both mean these statements are logically equivalent. For this line, I want to highlight a good general strategy for finding contradictions is to find that something that you assumed turns out to be false. So something is both true and false. That's not possible in math. But you can also get contradictions by showing something that is obviously false, like 0 equals 1. Note that this doesn't work in reverse. You can't show that something is true by showing that your assumptions lead to something that's obviously true, like 2 equals 2. I can't explain why in the 30 seconds I have left, so you'll just have to be left with that's not how math works. Read the readings if you want. So that's the end of the first lecture of this course. Remember that office hours are right after class in my office, and that class is 4 times a week. So I'll see you all tomorrow.